All right. So I want to begin this video with something that understanding mathematics is relatively easy, but being able to do mathematics is a different ball game altogether. And I'm so pissed at this topic I'm covering today because it costed me some very crucial marks in a test. So it is Auth G. So what is this Auth G? Auth G, let's straight away dive into it. Auth G is a group actually. And what kind of a group? Let's take an example, I guess. That would be better. So let's take Z6. Okay. Finite group, cyclic, order 6. Okay. Now, Auth G is basically the group of automorphisms of G on itself. Automorphism is an isomorphism from G to G. Like an isomorphism could be from G to G dash. And when this G and G dash, they are basically the same group. If G to G, we find an isomorphism, it is called an automorphism. Okay. Now, okay, there is one more thing, inner automorphism. And that is basically conjugation. Looks like a conjugation. So we take an element from the group and then we define a function. So isomorphisms, homomorphisms, automorphisms, these are basically functions. So if I say, let's say phi is my isomorphism, homomorphism, whatever, if phi is that function and if it is satisfying this property, then it is called a homomorphism. And if it is a bijection, then it is an isomorphism. And if it is unclear, let me know in the comments. I'll make a separate video on this. But for this video, I am assuming that you already know this. Now, phi of AB, yeah, you know this. Okay, I'll not go deep into this. Now, G, when our function is like, say, phi of G, it gives us A inverse G A. Okay. So basically conjugation by an element, by all the elements. Okay. So this is the inner automorphism, which implies that we took the elements. Okay, elements, obviously it will be of G only, but we compose this left and right multiplication and we define a bijection. Okay, is it making sense? Because I just got a doubt. If we take in a G from a group and we take some random A from the same group and we do this AG A inverse. Okay, first thing, see this A inverse AG and AG A inverse. I mean, it depends on the A, but And these are something, this is an equivalent thing written, not much of a difference. I think an example would be better. Z6 was the group, so 0, 1, 2, 3, 4, 5, right? Let's take our G to be 2. Let's take A as 1. So A inverse will be 5, 5 and 1, 6. Yeah. Or I can take my A as 5 and A inverse as 1, right? It will still give me an element. Okay? So, like if this is Z6, this is again Z6, and let's say phi is the isomorphism, the function that we have defined, then let's say if I do, okay, let's, for the sake of differentiation, let's take it A1 and A1 inverse, and this has A2 and A2 inverse. So A1 G A1 inverse gives us 1, 2, 5. The group operation is addition, so we'll put a plus sign. Now 5 and 2, 7 and 1, 8, mod 6 is 2, right? Okay. And similarly, if I do A2G, A2 inverse, then I'll just get 5 plus 2 plus 1. Again, I'll get 8, and 8 mod 6 is 2. However, this is a very simple example. See, our group is abelian, and every element has just one conjugate. So it will be mapped to itself. No matter what we choose to be A1, A2, it does not matter. In an abelian group, every element is the conjugate of itself. And this is because to find conjugates, we do this GHG inverse. And if the group is abelian, then they can switch positions and it will annihilate, it will turn into identity, and we'll be left with H. Okay. Yeah, so yeah, I think it is pretty simple. In a cyclic group or in an abelian group, we can do this. We can define this as the inner automorphism by conjugation. Okay. And now let's come to the more important things. I mean, this is also important, but the star of today's video, Aut Z6. But let's take a particular example first. So I said that this in itself is a group, okay? And you'll see how different it could be from Z6. I'm not sure yet. I've done examples of Z8 and Z10, but not of Z6. Let's see. Okay, so how to begin? I'm sorry again, I'm not structured, but I was very occupied with something. Now, this is a group. So what are the elements of this group? See, the first element is this itself, this phi, which is the inner automorphism. That is conjugation. Okay, so this is this isomorphism is an element of this group, automorphism of Z6. So Aut G contains isomorphisms. Aut G is a set of all phi such that phi is an isomorphism from G to itself. Okay, again, collection of all the isomorphisms. That means one onto homomorphisms. Okay, I did not. This is the definition of automorphism. And yeah, let's just add isomorphism as well here as a condition. So you get the idea, right? All the isomorphisms from a group to itself, when formed into a set, will give us a group actually. And that group is called the automorphism of G. Okay. Now a group has identity, a group has inverse. A group has identity, its elements have inverses, it satisfies closure, obviously, so all those. So now let's see, our G in this case is Z6. So let's say Z6 to Z6. How many isomorphisms exist? Before that, how many homomorphisms exist? I hope you already know this. It is the GCD of these two, which is 6. So in this case, we have 6 homomorphisms. And if you want me to, I can make a video on this. But no, why would I? There are videos on this. But I could not find a nice video on automorphism. Anyway, that is why I'm making this. So 6 homomorphisms from Z6 to Z6. And now how many of them will be isomorphisms? For an isomorphism, each element should have a unique image, and it has to be a bijection, 1, 1 and on 2. So of course we have Z6 and Z6. The cardinality, the cardinality of both these is same. So how many 1, 1 on 2 functions can be defined? 2, which is, see, okay, look, from Z6 to Z6, we can define phi of x to be x, or phi of x to be 5x. Or in simpler terms, let me do a little change. Either 1 can map to 1 or 1 can map to 5. Now let's take this as phi1, this is phi2. So this is our first isomorphism. This is the second isomorphism. Why will this be an isomorphism? Because in this particular group, 1 is a generator of the group. So we can operate 1 6 times and get back to the identity. So we will get 6 images of 6 elements. Am I confusing? Let's do this. Okay, so phi1 is 1. What will be phi2? Phi2 should be phi of 1 plus 1. And by the definition of homomorphism, this should be phi of 1 times phi of 1, which is 1, 1, and operation is plus because even the other group is also Z6, same operation. So this is 2. What am I doing, man? This is This is the identity map, right? So yeah, it is like phi1 is sending x to x and phi2 is sending x to 5x. This is more interesting. Let's see this. Okay, let me put phi1 here. Okay, so phi2. Phi2 is sending 1 to 5. So phi2 will send 1 plus 1 to, let's see, let's break it. Phi2 of 1 plus phi2 of 1, which is 5 plus 5 mod 6, which is 10 mod 6, which is 4. So 2 is being mapped to 4. Okay. Similarly, phi 3, sorry, no, phi of 3. So this is phi 2 is 4. Phi 3, we can write it as phi 2 of 2 plus phi 2 of 1. Also observe. Okay, don't. Yeah, just give me a moment. 4 plus phi of 2 is 5, which is 9. 9 mod 6 is 3. Okay, nice. Yeah. Yeah, now observe what I was saying. See, phi of 2 is 4. So what is the inverse of 2? It is 4. Phi of 4, it will come out to be 2. Let's verify it. 5, I'm sorry, I should write 2 here. Right? Phi of 2 plus phi of 2, which is 4 plus 4 mod 6, which is 8 mod 6, which is 2, right? So did you see what just happened? 2 was mapping to 4. So 2 inverse mapped to 4 inverse. Basic property of isomorphism. Okay, sending inverses to inverses. The inverse of 2 was sent to the inverse of the image of 2, right? I hope this is clear. Okay, so what we figured out is that there are two isomorphisms, long word, two isomorphisms from Z6 to Z6. Okay, wait, Z6 to Z6. What does this mean now? That our Aut Z6, the group that is supposed to contain all the isomorphisms from Z6 to Z6, it will have two elements, phi1 and phi2, where phi1 is the identity map. Identity map. Map is also a function, if you remember. So just the identity function. And phi2 is the second isomorphism that we found. Okay. So automorphism of Z6 contains two elements, right? So Aut Z6 is actually isomorphic to Z2. Any group with two elements is isomorphic to Z2. That's why. Right? I hope I gave you some insight into this Aut G. And now let's see one more example. Actually, two more examples. Let's find Aut Z10 And then we will conclude one more thing. Aut Z10. Okay. So how many isomorphisms from Z10 to Z10? From Z10 to Z10, what we are doing is that we are finding the numbers that are co-prime to 10. Elements with order 10 in Z10, which are 1, 3, 7, and 9. So if a map sends 1 to 1, that means if a map sends x to x, this map will be the identity map for the group Aut Z10. Okay, this function will be the identity element of this group. And then second one will be phi of x. Let's name it phi 2 or phi 1. Okay, let's name it phi 1 of x, or no. Yeah, I don't have those many symbols, xi and all. Okay, anyway, let me focus. So phi 1 of x, which is doing this to the elements. This is the second. This is the first isomorphism, which is the identity. This is the second isomorphism. This will be the third isomorphism. And this will be the fourth isomorphism, 9x. Okay? Why? In this group, it is easy to see and understand because these elements have order 10. So we can operate them 10 times. Okay? 10 distinct, we know, right? Phi of a to the power k is phi of a to the power k. This is a property of isomorphism. Very easy to prove. Phi of a, okay, this means phi of a, so on, k times. I don't know why I'm proving this. It is very simple. And we can break this phi of a by the basic property of isomorphism. Phi of a k times, right? So we get phi of a k times. So by this property, we can say that all the generators of Z10, if we define isomorphisms, taking them, they will form a 1-1 onto map onto Z10, right? So now this Aut Z10, this group will contain phi 1, phi 2, phi 3, and phi 4. Okay? Where this is the identity map. Identity element, also the identity element. Okay? Now, now interesting. So we got a group which has 4 elements. So what is it? K4 or Z4? And how do we find it? Well, if there is an element of order 4 in this group, then it will be Z4. And if all 3 have the order 2, then it will be K4, right? And how do we find it? Well, we just operate the element on itself to check what is its order. For this, we need to find the order of the element, right? So phi 2 operated on phi 2. That means phi 2 operated twice on x, of course. So what is phi 2 doing? It was sending x to 3x, right? And phi 2 of 3x will send it to 9x. which Aut 6 means what? Again 3x, right? If I'm not wrong, is it? No. See? Or is it right? No, I'm confused. And there should not be a confusion. But no, confusion is good to understand things. I think this is right. But what will happen next? 9x. So it mapped 1 to 9. And our group is, damn, it is Z10. I'm sorry, it's not 6, not 10, which is 9 itself. Okay. Did we get identity? Not yet. We haven't. Well, this is enough for me to conclude that, okay, this group is not K4 because every element of K4 has the order 2. And I just operated phi 2 twice and I'm not getting identity. But okay, this is 9x. So let's operate 3 times. So what will we get? Phi 2 of 9x now, which will be 27x. Mod 10 will be 7x. Okay, still not identity. Let's operate it one more time. 4 times. 7 into 3 is 21x mod 10, which is obviously x. And I am back to identity. Okay. So phi 2 has order 4. Enough for me to conclude that wait a minute, that this thing, okay, this is contrast. This thing, I'm sorry for this. This thing is not K4. It is indeed Z4 because it has an element of order 4. So Aut Z10 is isomorphic to Z4. In a similar way, I think, okay, let me conclude one thing right here. See, how are we forming this? We are looking at the generators of the group, right? Here also we looked at the generators of Z6, which were 1 and 5. So it means that every number in this specific example of Zn, every number that is coprime to n, every number that is coprime to n will be a generator and will give us a unique element of this automorphism, the group of automorphisms, right? Similarly, in this case, 10 has 4 generators. So all those 4 generators gave us 4 isomorphisms which formed elements of the automorphism of Z10. So the generators give us the elements of the automorphism group, the group of automorphisms, right? Aut Z10. Okay. What does this mean? How do we find the generators? By using the Euler phi function, right? Phi of 6, which is 6, 1 by 2, 2 by 3. I hope you know this. 2 generators. Similarly, phi of 10 is 4. So Automorphism of Z10 is isomorphic to Z4. Automorphism of Z6 is isomorphic to Z2. And we know that this is also isomorphic to U6, no? Because U6 is the group which gives us elements co-prime to 6. Okay, similarly here U10 is the group that gives us elements isomorphic to co-prime to 10. Okay, so we can safely conclude that automorphism of Zn is isomorphic to Un. But this in itself is a group whose elements are isomorphisms from Zn to Zn. Right? Yeah, I think this is enough about this group. I hope it makes your understanding a little better. Also, I hope you remember what I said in the beginning. Doing maths, understanding maths. Two different things, man. So, yeah, keep practicing, keep getting better. The more you do, the better you understand, the better you are able to apply. Yeah, so let me know if you need help with anything in this or anything. Okay, I'll end the video. Thanks.